Here we go. Okay, clear?
Is it possible to define those matching conditions in general terms, like that the metric tensor is continuous and differentiable?
You need much more than that. So, yeah, the matching conditions that I'm imposing, where you have this term-by-term matching, is much stronger than, C1 at an interface.
But what does it mean in terms of the full metric here? Suppose that ideally you have exact metric tensor here and exact metric tensor here. So what are they supposed to?
So I'm assuming the mildest thing I can, which is literally just the matching condition. If I perform this expansion, say I had the exact metric, and I perform this expansion of it and this expansion of it, and then re-expanded them both, they match order by order. So that actually is the assumption I'm making, this matching condition.
And without the expansion,
so you can put in a much stronger requirement.
No, I mean, but without expansion.
No, my requirement is at the level of the expansion.
I see. So you cannot define it without the expansion.
This mild requirement I cannot. No. You can impose much stronger conditions on smoothness. But those conditions actually rule out cases of interest. So I would say those are too strong, and this is the one we want to assume. Okay, so in terms of the self field versus regular field, this is in close analogy to, say, electrodynamics. So in electrodynamics, if you have a particle zipping around, or a charge distribution zipping around, you have a local Coulomb field that just is moving along with the charge distribution. And then you have a radiation field. And the radiation field satisfies the homogeneous equation. So this is in close analogy with that. Here I'm showing kind of pictorially the decomposition. So we have the full metric here of the full physical space-time with the body moving through it. And we're splitting that up into the self field of the body, which is locally determined by the object's multipole moments. And then we have this effective metric, which is the external background metric G plus this regular field. So this effective metric is a vacuum solution, even at the representative world line of the particle, or of the small body. And it's nice and smooth and slowly varying. And it's only determined once I impose boundary conditions on this effective metric. So in practice, we would usually impose retarded boundary conditions far away at scry minus and at the event horizon. So we have this nice clean split based on a local multipole decomposition around the particle or around the small body. Now, the local analysis solving the Einstein equation also gives you an equation of motion for the representative world line of this small body. So I showed you how we define this representative world line using the mass dipole moment of the body, basically, or of the background metric in the inner expansion. The Einstein equations then tells you an evolution equation for that trajectory, for that representative world line. At first order, for an arbitrary compact object, so this could be a neutron star, it could be a black hole, it could be anything, it could be something more exotic. It just has to be compact. This is the equation of motion you get from the Einstein equations. So left-hand side is the covariant acceleration in the external background metric. Then this thing here is what we call the first order self force. So it's expressed in terms of the regular field. It's a derivative of that regular field. And then we have a finite size effect, which is the spin of the small body coupling to the external curvature, the Riemann tensor. And by doing some simple rearrangements, you can show that this equation is entirely equivalent to the motion of a spinning test body in this effective metric G plus HR. So this effective metric is, as far as the body is concerned, is basically just an external metric where the body is moving as a test body in that external metric. Now, at second order, we still don't have actual fundamental results for the motion for a generic compact body. What we do have is the equation of motion for a spherical, non-spinning body. So again, what we have is things involving the regular field. Here, this regular field is epsilon HR1 plus epsilon squared HR2. It's the sum of all the terms in the regular field. And again, you can easily show that this equation is totally equivalent to the geodesic equation in this effective metric. G tilde is background plus regular field. So for a non-spinning spherical body, this effective metric we've found from the local analysis of the Einstein equations is really acting like an external kind of effectively physical metric. Yeah.
When you're talking about the evolution of a compact body in a space-time, like submerged in a space-time, are we taking like slices of like Riemann and hypersurfaces and then like the ADM decomposition or something, or are we talking purely continuous analytical approach?
So this is all in 4D. There's no slices yet. I will introduce important slices a bit later, but at this level, this is totally four-dimensional, no slices of anything.
But this evolution, you're talking about just like points to points throughout the space-time, or?
No, so this is proper time on this representative world line. So this stage is not looking at information over a whole slice of anything. It's just on the world line. Just how is this world line evolving? Yeah. Okay, so we can really think of this effective metric G plus HR as an effectively external, like pseudo-physical metric. It's the metric that the body is in free fall with respect to, if it's non-spinning. Yeah. This spin tensor is defined from the ADM angular momentum of the inner background spacetime. So the supplementary condition at this level is just coming from the mass dipole moment vanishing. So yeah, at this level, this order in perturbation theory, the common supplementary conditions, P dot S are 0 and U dot S are 0, they're the same at this order. And basically I'm using either one of those. Okay, so if I did have an extended body, then we do know what effects would appear in this equation of motion. I mean, if I had a non-spherical extended body, then I would know that here I would just have not just spin, but I would also have the quadrupole moment of the body appearing at this order, second order in the equation of motion. And just to emphasize, everything I've derived here has come from the vacuum Einstein equations outside this small body. I haven't said anything about a point particle. I haven't introduced any singularities yet. Everything's perfectly finite, smooth vacuum geometry outside the body. But now I am going to introduce a singularity because it's convenient for me. So we really don't care about the details of the internal, inside of the body. We don't care about any fine details. All we care about is how it's influencing the metric on larger scales outside of it. So what we're going to do is just throw away that region. We're going to take the analytical expressions we have for the self field in the buffer region, and we're just going to extend those down just analytically. We have a formula, it's 1 over s squared plus 1 over s whatever. Just analytically extend that down to the representative world line, where now we have an actual singular field. But we haven't changed anything in the buffer region or outside, and we haven't changed the effective metric even on the world line. The equation of motion that we obtained in terms of the effective metric, nothing's changed. It's all still exactly as it was. I've just thrown away irrelevant details in this tiny, tiny region around the body.
It is the logic here that you start with the self field and
Yeah.
derive quantities there
Yeah.
and then, okay.
Exactly, yeah, yeah. All the derivations are done before this, yeah. So what's happened here is that I've replaced this extended body with a singularity in the space-time geometry, which we call a puncture. So I've kind of punctured the space-time manifold. This name was inspired by numerical relativity punctures, but it's not really quite the same. And so this puncture carries the local information about the body. It encodes the multipole moments, it encodes the motion of this representative world line. Okay, now once we've done that, how do we make use of it? The idea is we have some local expansion for this self field. We're going to truncate it at some finite order in powers of distance. And that truncated expansion I'm going to call the puncture field. Then I just define this residual field that's the physical field minus the puncture. And I design things such that the residual field and its first derivative on the world line are identical to what I call the regular field and its first derivative on the world line, which means I can use this residual field in my equation of motion for the world line without making any errors. It's exact. Then in some region around the world line, I solve field equations for the residual field, not for the physical field. So I'm starting with vacuum equations that are valid everywhere up to the world line. I'm then just moving the puncture to the right-hand side of the field equations. So now I've got residual fields on the left, and I've just moved puncture fields to the right. And then outside of this region, I solve the vacuum equations for the physical fields, H1 and H2. Now, all of this is very closely related to point particles, but not completely identical to. So how is it related to point particles? Well, we have a bunch of entirely mathematically equivalent formulations here. So one thing we can say is we can formulate things as a free boundary value problem, like I discussed last lecture. We can say everywhere except precisely on the world line, we're solving a vacuum equation for H1. I won't get into H2 in this discussion here. And arbitrarily close to the world line, you have to recover this local form we found. That's kind of a boundary condition, an asymptotic boundary condition as you approach the world line. Now, another approach would be the puncture scheme I described on the last slide. So here, we've moved the puncture to the right. We've just taken this vacuum equation, moved the puncture to the right, called this Einstein tensor of the puncture an effective source. So naively, this is only valid for points off the world line. But then we just extend this field G1 of HP1 by continuity just down to the world line, which is equivalent to saying I want my residual field to be continuous and differentiable on the world line. And so then this equation is valid for all x, not just on the world line. I'm sorry, not just off the world line. Even though I started with a vacuum equation, it's only valid off the world line. I now have an equation for the residual field that's valid everywhere. Another, again, completely equivalent formulation is that G1 of H1 is a delta function, a point particle source. So you can take this local field that you derive from the vacuum equations outside this small body, you extend it down to the world line as I described, and then you can just calculate G1 of H1. And what you find this isn't that we're assuming this. What you find is that this is G1 of H1, this delta function. So if you haven't seen this form of a delta function source, just think of using one of these deltas to get rid of this integration over proper time, and then you're just left with a three-dimensional spatial delta function that diverges at the particle's position. And so we can call this thing T1. So here we're defining T1 to be whatever comes out of this. So this is actually a derivation of the validity of a point particle approximation. And all of these are going to give you the same total H1. It's easy to show that. And all of these are coupled to my equation of motion for Z in every case. Now, that might look confusing because in one case, I had G1 of H1 equal to a delta function. And so if I start with that and then move my puncture to the right-hand side, which should be a perfectly allowed thing to do, then I have this equation. I've got a T1 and I've got a minus G1 of HP1. But I also said that this equation is valid everywhere, where there is no T1. I've just moved the puncture to the right-hand side of the vacuum equation. But you can show, in fact, these two effective sources are identical. And what's different here is the interpretation of derivatives in this G1 versus derivatives in this G1. So in the top, those are just ordinary derivatives of ordinary functions. I'm evaluating the derivatives of a known function HP1, and then just extending the source to the world line just by continuity. So just by taking the limit from off of the world line. Whereas down here, these are distributional derivatives. So fundamentally different derivative. And what happens when you treat the derivatives as distributional, then you get a delta function out of this G1 of HP1 that exactly cancels the other delta function, and you're left with this effective source that's identical to the one up above. So it's a kind of mathematical subtlety. But the main point is all these things are totally equivalent to each other. Okay, so what I've just shown you is how we can calculate the residual field in a region around the small body, or a region around the world line, and then the physical field everywhere else. But I also showed that you can just formulate an equation for H1 where you have a delta function source. So you could just solve that equation directly and get H1 out. And in practice at first order, that is usually what is done. You solve for the physical retarded H1 sourced by that point particle. You don't, at first order, you usually don't use a puncture scheme. At second order, we've only ever implemented puncture schemes. We've never done things with point particles. But you do need to extract the regular field and its first derivative on the world line, because you need to be able to solve that equation of motion for the world line, where you had a derivative of the regular field on the right-hand side. So if you calculate the physical H1, which is singular on the world line, you need to then extract the regular field. The way that's usually done is using a method called mode sum regularization. Because I'm so far behind where I want it to be, I'm going to entirely skip that. But the idea is you take your singular field, or sorry, your physical retarded field, and you subtract this singular field. But you don't do it where you've got the four-dimensional quantity minus the other four-dimensional quantity, because that would require canceling singularities that would be numerically quite delicate. Instead, what you do is, when you're solving your field equations, typically you're decomposing into some basis of spherical harmonics or spheroidal harmonics centered on the big black hole, not the small black hole. And at the level of individual harmonic modes, the retarded field and the singular field are both finite. So you do the subtraction of the singular field from the retarded field mode by mode, LM mode by LM mode. But I'm going to skip that. Now, what has happened? Yeah, I'm going to skip that and just emphasize the big picture theory, what's happened. So we started with something where everything is perfectly finite, there's no singularities. We introduced that singularity by hand because we wanted a simpler problem to solve, but we introduced it in such a way where we can control the singularity and we know exactly how to calculate the specific field HR that is driving the motion of the small body. And what comes out of all of this is a picture of a test mass moving around in free fall in this effective metric. That's a vacuum metric. Okay, now that's a bit of an awkward time to take a break, but yeah.
So, does it make sense? Does it make sense to say that this trajectory is not included in the manifold because it's singular?
Depends which manifold you're talking about. So we had three manifolds. So we have the physical manifold of the perturbed physical spacetime. We then had the manifold of the background metric. That manifold is diffeomorphic to the manifold of this effective metric, and that's where the world line lives. Yeah. So the world line is not, if you have a black hole, if you have a material body, then it's fine to have a world line inside. If you have a black hole, then this world line is not in the physical spacetime, and it's not in this manifold of the inner expansion. It's only in the other manifold of the outer expansion.
I had in mind that also the right is a problem of positive if you signals to them, so we have to cut out light holes. But I understand that this scheme takes care of that and it allows a nice way to continue signals through this.
Yeah. Okay. Okay, I'll continue on and try to find a decent place to take a break. So we're now on to lecture 3. So we've derived everything we need locally through second order. So I didn't discuss the puncture scheme at second order, but it works just the same. And I didn't discuss the point particle approximation, not approximation, the point particle formulation at second order. That's actually very mathematically subtle, and it hasn't been used in practice yet. Everything's been done with punctures at second order. Okay, but that's all local information around the small body. Now we move on to the global problem. We've extracted, field equations for how we can incorporate the small body. Now we want to solve those field equations in particular background spacetimes. And for us, background spacetime that we're almost always interested in is Kerr. So we're taking the big black hole, or taking the big body to be a Kerr black hole. And so we want to solve field equations in that background. So this is what came out of the local problem. These are the field equations we want to solve. Here I'm writing things in terms of a puncture rather than a delta function source, but same idea. So we have a field equation at first order for first order residual field equation at second order for the second order residual field. And then those field equations are coupled to this equation of motion. Here I'm ignoring the spin of the secondary. It's very easy to add on top of all this. On the left-hand side, I basically have a D'Alembert, a curved space-time wave operator. And in the Lorentz gauge, it really is basically just that, the D'Alembert. Then on the right-hand side, well, I've got the thing coming from the puncture, but I've also got this quadratic field that's basically the square of derivatives of the first order field. So now we want to solve this coupled set of equations in the external geometry of the Kerr black hole. So I'm going to break this up into 2 sections. In the first section, lecture 3, I'm going to be focusing on orbital motion. So I have some force causing the motion to be non-geodesic. What's the form of the solution? How do we deal with that? Then in the final bit, I'll talk about actually solving the field equations coupled to that motion. So let's start with just geodesic motion, just 0th order, before we even add the cell force. So here's the Kerr metric in Boyer-Lindquist coordinates. Hopefully everyone has seen this at least on Wikipedia or something. It's a lot more complicated than Schwarzschild, but doesn't matter too much. The main thing I want to emphasize is just the introduction of this quantity capital sigma and capital delta. Capital delta equals 0 is the event horizon. And this metric has 3 symmetries. So it has 2 killing symmetries, 2 isometries. One is the time-like killing vector, and one is the axial killing vector. So you can see the metric doesn't depend on Boyer-Lindquist t or Boyer-Lindquist phi. So we have killing vector associated with each of those coordinates. So here's the ordinary killing equation for those vectors. And then we have a hidden symmetry, which is the existence of a killing tensor, which satisfies a similar kind of relationship as killing vector. And there's a missing L in killing here. So for each of these symmetries, we get one conserved quantity on a geodesic. We get the energy, we get the azimuthal angular momentum, and we get the Carter constant. So one per killing vector or killing tensor. We also have the constraint coming from the fact that if we use proper time as a parameter, then the contraction of the forward velocity with itself is just -1. So we have 4 equations here that relate the forward velocity to a constant. So we have the forward velocity related to the energy here, the forward velocity related to angular momentum, forward velocity related to Carter constant, and forward velocity related just to this constraint. So 4 equations and 4 components of the forward velocity. So we can invert that and get equations for the forward velocity. The equations look like this. So this capital sigma is the one I introduced on the previous slide, r squared plus a cos squared theta, or whatever it was. And except for that factor of sigma, you can see you almost have a decoupling between the different components. So the radial component of the forward velocity squared is just a function of the orbital radius. It's just a function of r on the world line, except for that capital sigma squared on the left-hand side, which is a function of r and theta. For convenience, I'm going to introduce z equals cos theta. So that's like a vertical measurement of inclination. And again, z almost decouples from r. The right-hand side here is just a function of z. But on the left-hand side, you've got that capital sigma squared, which is coupling r to z. Then you have equations for t as a function of tau and phi as a function of tau. Again, on the right-hand side, you have basically something that's nicely separated between a function of r and a function of z in both cases, but then you get this coupling again through capital sigma. Now, the functions capital R of r and capital Z of z are actually nice, simple polynomials. And you can factor those polynomials. So capital R is a 4th order polynomial being factored like this. Capital Z is another 4th order polynomial, but with degenerate roots. So this immediately tells us that we've got turning points where the right-hand side goes to 0. So for a bound orbit, you're going between a maximum r and a minimum r, back and forth, back and forth. And same for z, for the vertical displacement from the equator, we're going between a maximum, minimum, maximum, minimum. Okay, and everything was nicely separated, nicely decoupled, except for that capital sigma on the left-hand side of all the equations, which was a function of r and theta. Now you can decouple everything. by adopting this new parameter, lambda, which is known as menotime. So we just say we've got a new parameter, lambda, satisfying the lambda d tau is 1 over that capital sigma. And as soon as you've done that, you've just eliminated all the capital sigmas on the left-hand side. So now we have a decoupled equation for the orbital radius. We have a decoupled equation for the inclination. You can solve those, each of those separately. Then you just substitute the solutions on the right-hand side here. And then you can solve for t as a function of lambda and phi as a function of lambda. So this gives a nice, compact way of solving the geodesic equation in Kerr. Once you know this structure, there's a lot of ways to parameterize the geodesics. So here's kind of a quasi-Keplerian way of doing it. So we know for a bound orbit, we're going between a minimum and maximum radius and a minimum maximum inclination. So let's just introduce manifestly periodic parameterizations of the orbit. So this is just exactly what you'd have for a Keplerian elliptical orbit. And this is a very simple formula for the inclination. On the top, I have the semi-lattice rectum, which if we had a true ellipse, we don't have a true ellipse in physical space, but we're kind of trying to write things like an ellipse. If we had a true ellipse, then that parameter p would be this distance here. The big black oval is the ellipse itself. And then we've got the eccentricity down here. And over one radial period, psi r goes from 0 to 2 pi. So you're going from maximum to minimum, back to maximum, or vice versa. And similarly, psi z is going from 0 to 2 pi over one period of the inclination. So from maximum to minimum, back to maximum. And you can write a one-to-one mapping between the parameters P, E, and Z max, and the parameters I mentioned before, energy, angular momentum, and Carter constant. So E, L, Z, and Q don't give you really an intuition for what the shape of the orbit is, whereas these give you some intuition for what it looks like. And you can also relate, or actually define P and E from these relationships, telling you the closest approach, RP, and the furthest distance, RA. So P is periapsis and A is apapsis. Yeah.
Sorry, how do you distinguish between prograde and retrograde orbits?
Yeah, so some pluses and minuses come in.
Yeah. So
Yeah.
Zmax doesn't have information about this, right?
Zmax doesn't. No. So prograde versus retrograde is coming into phi, the motion of phi, which isn't actually even being written here. Okay, so this is a quasi-Keplerian description, and you get formulas for the evolution of this phase, psi r, and so it's just a function of psi r itself, and similarly, evolution of psi z. So I mentioned in the first lecture yesterday morning that we have three distinct periods of motion or frequencies of motion in Kerr. What that means is that the period of r and the period of phi is incommensurate. So one isn't the ratio of the two periods is not a rational number in general. And similarly, the ratio of the radial period and the inclination period is also generically incommensurate. So when you say that the r and phi periods are incommensurate, what that means is you have precession of periapsis, just like you learned in the very first GR course you took when you learned about the precession of the perihelion of Mercury. So here's kind of a weak field, mild precession. So the orbit is not coming back to itself, it's precessing with time. This is a much more extreme example. This is what we call a zoom whirl orbit. This is actually an orbit in Schwarzschild, not even in Kerr. And so what's happening here is you come in, zoom around the center. You can make it zoom arbitrarily large number of times, infinite number of times, any number you like. Then it comes back out, comes back in, zooms, comes back out. So it's zoom whirl. So that's you know, the complexity of strong field dynamics manifesting itself. So that's what you get from r and phi motion being incommensurate. This is what you get from z and phi periods being incommensurate. So here we're actually fixing the orbital radius. The orbital radius here is constant. And in that case, all you're getting is you're on a sphere, basically. So these are called spherical orbits. And just the plane is moving up and down like this. So again, on the left, we have a kind of mild example of that. And on the right, we have a much more extreme example. This is the generic case. So 2 slides ago, what I was showing you was an equatorial orbit with no z motion. 1 slide ago, I was showing you z motion with no radial motion. Once you have both of those motions, you get something like this. Generically, this is actually space-filling orbit that completely fills up a torus. You know, it gets arbitrarily close to any point inside that torus. And if you have any interest in these kinds of orbits or in gravitational wave modeling that uses this, I recommend checking out these packages and tutorials online. You can just generate these orbits for any parameters you like and just look at what happens. Okay. Now, I introduced those 2 phases, psi r and psi z, that were running from 0 to 2 pi over a radial period and 0 to 2 pi over an inclination period. And we can write the evolution equations for this geodesic in this kind of simple compact form. So I'm going to introduce 4 of these angles now, 4 of these phases. The psi r and the psi z that I already mentioned. I'm just going to call t psi t. I'm going to call phi psi phi. And then the equations, the evolution equations for those phases just look like this. We have functions of psi r and psi z on the right. We don't have any dependence on psi t or psi phi. That's coming from the killing symmetry of the background. You don't never depend on t and phi. And then these capital J's are just my constants of motion. They could be E, L, and Q, or they can be P, E, and Z max. So fine either way. And those are constants, so we just have 0 rate of change. But there's actually a better way of formulating all this. We can transform from these psi's to a different kind of phase called Q, where rather than having a rate of change that depended on the phases, this one has a rate of change that only depends on the constants of motion, P, E, and Z max. So these are what I mentioned, or these are closely related to what I mentioned in the very first lecture. So these are action angles that have exactly constant rate of change, constant frequency. And what this Q is, it's an averaged version of the psi. So this frequency, upsilon, is an average of the function. Let's see if I can aim better over here. It's an average of this function here. So you're just getting rid of the oscillatory things and just picking out the mean frequency. And this isn't throwing away physics. We still have all the physics. This is just a transformation of coordinates. Coordinates on phase space, not in space-time. So we can actually write down this transformation. It's an invertible transformation. Now, the orbit in Boyer-Lindquist coordinates, so in space-time coordinates, is actually known analytically as a function of these q's and these j's. The analytical form is made up of Jacobi elliptic functions, but it's closed form in terms of those special functions. But we can do even better. So the action angles on the previous slide were based on having constant menotime frequencies. Menotime is not physical time. It's just this convenient parameter that we found to decouple the geodesic equation. What's going to come out in the waveform, what we can actually measure, is frequencies with respect to Boyer-Lindquist time, the time of an inertial observer at infinity. That's the physical time that we're interested in. That's what we measure in the waveform. So rather than using this Q, we can change to another action angle, curly phi, that has a constant frequency with respect to Boyer-Lindquist time. So these are the frequencies that appear directly in the waveform. The expressions for the orbit in terms of these curly phis is much more complicated than in terms of the menotime action angles Q, but this is the one we're actually interested in for extracting the waveform and evolving everything. So we now have, and once you base everything on Boyer-Lindquist time, you can throw away one of the phases because one of the phases just was t itself. So now we're just writing everything in terms of t. And this gets back to the question earlier of foliations of space-time and evolution from one foliation to the next, or from one slice to the next. At this stage, we're going to start doing that using this actual global choice of time. We're now going to be defining basically our orbital quantities as functions on a slice, not just as functions on a parameter along the world line. And then the whole system's going to be evolving, including the orbital information from slice to slice. So we now have these three curly phis, these three constants of motion, and the frequencies are just ratios of the menotime frequencies. And they're, again, uniquely identified by the constants of motion P, E, and Z. Okay, where are we at? Maybe that's a good time to take a break, just a 5-minute break, because I think I won't finish this lecture within the hour. Yeah, so 5-minute break now. So far in this lecture 3 was on geodesic motion. Now let's move on to what happens once we add the perturbing force, the self-force. So rather than having 0 on the right-hand side here, like we would have for a geodesic, we now have a first-order self-force, a second-order self-force. We would have spin and quadrupole terms as well in general, but I'm just going to ignore those here. Now, we had defined this map between the coordinate trajectory and forward velocity to these other parameters describing a geodesic. If we just take exactly that same map and apply that map to the perturbed motion, then we get equations like this. So remember, at 0th order, I just had a frequency that was a function of the constants of motion. Now I have a correction to that, order epsilon correction. And this is a function of not just the j's, but also the phases, the action angles, curly phi. And then down here, remember I had exactly 0 for a geodesic. Now I have an order epsilon correction. And this is a function of the j's as well as the curly phis. And then also I have epsilon squared correction, which again is a function of both the j's and the curly phis. So you could just say, okay, that's it. This is what I'm dealing with. But that's quite bad. It'll be very bad once we look at the field equations. But it's bad even if you just think about the motion. Because remember, the reason we were setting up these curly phis and these j's was to not have any oscillations on the right-hand side. So when I had things in terms of the size, the phases psi, I had a dependence on those phases on the right-hand side. And so I was mixing oscillatory things with constant things. Now I'm mixing oscillatory things with slowly evolving things. I would much rather have a set of parameters J that are only slowly evolving with no oscillations, because I'd like to cleanly split oscillatory things from secularly changing, slowly changing things. So I'm going to do another transformation. So I think this is the fourth or fifth transformation. We have oscillations all over the place. I want to get rid of them. So I'm going to change from my curly phi's and my j's to tilde versions of them, where now I'm going to have no oscillations on the right-hand side for either of these ODEs. Everything is only a function. These should be tilde j in here, tilde j in there. Everything's tilde. So I've found a transformation. This one's called a near identity averaging transformation. I found a transformation that eliminates the oscillatory dependence on the right-hand side. And I now have a clean separation between phases that are basically evolving at a constant rate, almost constant rate, and parameters j tilde that are just slowly evolving with no oscillations. So I've very cleanly separated things into phases and slowly evolving parameters. Now we can link this back to what I showed in the first lecture, where I talked about the motivation for this nomenclature of adiabatic or 0 PA, and then post-adiabatic or 1 PA. So for that, I showed you formulas for an asymptotic expansion of, I don't remember if I called it phi tilde at that point or just phi, but it's exactly this expansion. So you can just take those coupled equations up above and basically see by eye that they admit solutions of this asymptotic form. So remember, I had 1 over epsilon times a 0 PA thing plus epsilon to the 0 times 1 PA thing. And similarly, we have an expansion like this for the orbital parameters. Here, T tilde is epsilon times T. So we've recovered what I showed on the first lecture yesterday morning. We've recovered this asymptotic form of the orbital phases. And by looking at what contributes to this capital G1 and this capital G2, you can also recover what Hinder and Flanagan described in terms of the dissipative force, first order dissipative force giving you this term here, and now we also say it gives you this term here. And then the second order dissipative force gives you this term here and this term here. And the conservative and oscillatory pieces of the first order force also contribute to this J1 and this phi 1. Everything I'm describing here isn't actually exactly what Hinder and Flanagan did. They were using different construction and different variables that weren't as nice for the field equations. But we get the same overall description that they had 15 years ago. So this is the formulation of the motion that I'm going to use. And just to emphasize, this omega A back here is exactly the geodesic omega A. But now it's a function of slowly evolving parameters J. So the formula omega A as a function of J is unchanged. It's just that those J's are now changing with time. Yeah. Mm-hmm.
There would be very strongly evolving to treat them as like quasi-constant things, or even not.
So The J's are adiabatic invariants. So they're changing only on this time scale 1 over epsilon. So the rate of change is proportional to epsilon. And then the phases are changing at order epsilon to 0 in the orbital period. Okay, everything I've said so far, remember I kept mentioning that the frequencies or the periods are incommensurate, meaning if you take 2 of the periods, their ratio is not a rational number. That's a generic setting. That's not always true. You can have the periods where the ratio is a rational number. And when that happens, we get transient resonances. So all these frequencies are evolving with time. And as they evolve, they can pass through a resonance where the ratio of 2 of the frequencies is a rational number. And rather than having that kind of space-filling curve that I showed before, now you get these pretty geometrical shapes. So this is an example where both of these are examples where the polar frequency divided by the radial frequency is 3 over 2. So these are the same resonance, but the orbits look totally different. And that's because the resonance depends not just on the value of this ratio, but also on the relative phase, phi r minus phi z. And so the only difference between these two orbits is that relative phase, different value of the relative phase. And you might think, okay, this is not generic behavior, this is very special behavior, maybe we'll just never see it in real inspirals. But in fact, we expect to see most MRIs pass through at least one of these resonances. And again, because oh no, okay, actually my time seems okay. So what happens as the frequencies approach this resonance? The passage through a resonance, so you don't get stuck on the resonance, the frequencies keep evolving until you pass out the other side. That passage takes a time of order 1 over square root of epsilon. So that's the time over which you have a significant effect on the phase. On that time, during that time, the rate of change of the frequencies is still order epsilon. So if the rate of change is epsilon and the time scale is 1 over square root of epsilon, then from one side of the resonance to the other, your frequencies have changed by square root of epsilon. So you come out with a frequency or a set of frequencies that differ from what you came in with by something of order square root of epsilon, which is a very tiny shift if you're looking at an MRI with 10 to the minus 5 epsilon. But after you come out the other side, you still have a long way to go before the orbit is over and the particle falls into the black hole. So you still have a time of order 1 over epsilon after the resonance, which means this tiny shift in the frequency accumulates to a big shift in the final phase. So we had a shift in the frequency of order square root of epsilon, and then we ran an evolution starting from there. That's another time 1 over epsilon. So you go from square root of epsilon down to 1 over square root of epsilon, which is potentially huge, a huge effect in the phase. Numerically, in practice, we actually find it's not that big, but still important for data analysis. Still is big enough to be important. So because of these resonances, we now pick up non-integer powers of epsilon, square roots. And now our expansion is more general. It includes every half power of epsilon. So this term here is coming from resonance. This term here is coming from resonance. Again, here's an example of a resonance, 3 over 2, omega z over omega r. So this is using kind of a crude approximation to the evolution, using post-Newtonian approximation for the evolution, but then using the exact Kerr geodesics to determine where the resonance is. And here we're seeing an example where we would start on the right. So this is effectively the size of the orbit on the x-axis. We're starting on the right and then evolving to the left. And the resonance occurs right here at this sharp divide. And the three different curves are Carter constant, angular momentum, and energy. And so you see they're kind of slowly changing, and then you get a big shift across resonance, and then you come out and then keep evolving. The fact that it looks like a really huge shift is kind of an artifact of the particular axis that's being chosen here. But this is the basic idea. Everything's evolving along, you get a jump, and then keep evolving. Okay, so that's everything I'm going to say about the motion. I'm now going to move on to solving the field equations and showing what comes out of this whole framework, the results that come out of the whole framework, and getting back to that waveform that I showed you yesterday. Okay, so we have a coupled problem fundamentally. We're coupling field equations, the Einstein equations, to the motion of this small body. I showed you what the motion looks like. That's already actually assuming a form for the metric perturbations. It's actually a coupled problem. You can't solve one without the other. So now I'm going to look at the field equations for the metric perturbations, and I want to design my field equations to work well with that formulation of the motion. I have to kind of formulate everything together in a nice way. And the idea is to use what we call a multi-scale expansion. So before I get to that, let me explain what goes wrong if you try to do just a naive Taylor series. So you just take your metric and you expand it in powers of epsilon at fixed space-time coordinates. Just an ordinary Taylor series in my small quantity epsilon. If you do that, then at 0th order, you literally have a geodesic source. You have a particle moving on a geodesic for all time. It's always on that geodesic. And you have small corrections coming from the perturbations. So for ages, the way people approached this was they said, okay, I'm just going to pick a geodesic source, put that in my delta function stress energy tensor, solve the perturbed Einstein equations, get the metric perturbation H1 sourced by that geodesic source, impose physical boundary conditions, meaning at infinity, we only have outgoing waves. At the horizon, we only have waves going into the black hole. We don't have any waves coming into the system. Just find H1. From H1, calculate HR1, the regular field, calculate the self force, calculate, invariant dynamical effects like perihelion precession, or the shift of the innermost stable circular orbit. Now, everyone knew over all these decades when people were doing that fundamentally this is not going to give you the full physical solution for the whole spiral, because your evolving orbit doesn't stay close to that geodesic. Say you have a geodesic that's at just a circle at 20m. Well, eventually your actual physical motion has plunged into the plunged into the black hole, and it's nowhere near that circular geodesic that you're using as your 0th order solution. So everyone knew that this formulation breaks down after some time. Once the particle has deviated significantly from that 0th order geodesic, you're doing an approximation that makes no sense anymore. And it breaks down specifically on this time scale 1/√square root of epsilon, which is called the dephasing time. So that's where the phases have evolved significantly away from what they would have been if you had a geodesic source. But let's just stick with that. Let's just say, okay, we're restricting ourselves to that time scale. What is the problem we're trying to solve? Okay, we've got a geodesic source, a point particle geodesic source, and we have the linearized Einstein equation for the first order metric perturbation. I could have easily made all of these lectures just on this one slide. So this is black hole perturbation theory, which has been developed, over the past 60 years. There's different formulations of black hole perturbation theory. They get used in cell-force calculations. These are the main ones. So I mentioned the Lorentz gauge a few times. Most, but not all, of the fundamental derivations of the equation of motion and these punctures and everything, most of that work was in the Lorentz gauge. So a lot of the analytical ingredients that go into a numerical calculation, a lot of those analytical ingredients are specific to the Lorentz gauge. So one approach is just write down the linearized Einstein equation in the Lorentz gauge in either the Schwarzschild background, if you have a non-spinning big black hole, or the Kerr background. So an advantage of that is, again, that a lot of the formulation work, a lot of the analytical ingredients that go in are in the Lorentz gauge. So you have a nice, easy way to use those ingredients. If you're in Schwarzschild background, because of the spherical symmetry, you can very easily decompose the linearized Einstein equation into a basis of tensor spherical harmonics. And then that separates the angular dependence, the theta phi angular dependence. And if you further go into the frequency domain, so you decompose into the Fourier domain, then you actually just have radial ODEs for a bunch of coefficients that depend on L and M for the spherical harmonic and on the frequency. A disadvantage of working in the Lorentz gauge is that it's not fully separable in Kerr. I mean, the field equation, the linearized Einstein equation, is not fully separable in Kerr. We don't have an equivalent of tensor spherical harmonics in Kerr. So that's a big disadvantage. Another option people have used is to solve the Reggie-Wheeler and Zerilli equations for some master functions that are just scalar functions. And then you can reconstruct the metric perturbations just by taking some derivatives of those scalars. So when people think about perturbation theory in Schwarzschild background, 99% of the time, they're talking about solving the Reggie-Wheeler and Zerilli equations. And that's, in most cases, a very simple way of approaching the problem. If you decompose again into spherical harmonics and frequency modes, then you just get one simple radial ODE for each of the coefficients, for each value of L, M, and omega. You just need to solve for two scalar functions that are decoupled, and then you get your metric perturbation. You're done. A big disadvantage of this is that Reggie-Wheeler's really is not defined in Kerr. It's only defined in Schwarzschild. And worse for cell-force applications is that the gauge that's used, the Reggie-Wheeler's really gauge for H1 here, is pathological if you have a point particle source. You get singularities that are not confined to the particle. You have gauge singularities that extend away from the particle, which is not ideal. If you're in Kerr rather than Schwarzschild, again, 99% of all black hole perturbation theory in Kerr is solving the Tucholsky equation. I like how they update that. Okay, so Tucholsky formalism is very similar to Reggie-Wheeler's Zerilli. Again, rather than solving directly for the metric perturbation, you solve for a scalar function. For example, the Weyl scalar psi 4. You can also solve the Weyl scalar psi 0. They contain identical information. And once you've solved the Tucholsky equation for this scalar, you can then reconstruct the metric perturbation by performing a sequence of integrations and differentiations. The big advantage here is that the Tucholsky equation in Kerr is fully separable in a basis of spin-weighted spheroidal, not spherical, harmonics. And that's why That's why it's used so widely. You just get nice, fully separated ODEs for each LM omega mode, just for one scalar quantity. It's a complex scalar, but still just one scalar quantity. Just like the Reggie-Wheeler gauge, there's a disadvantage to this. When you perform this metric reconstruction to get your H1, it comes out in a gauge that's pathological if you have a point particle source. Again, your metric perturbation then has a singularity, a gauge singularity, that is not confined to the particle, but goes far away from the particle, which causes a lot of difficulties.
Are the singularities only for particle-like sources?
Any singular source, yeah. So it could be a string, you'd still have singularities.
Something smoothed out wouldn't lead to singularity.
Yeah, then you have no singularities, yeah. So in fact, if you use a puncture scheme and do metric reconstruction from Tucholsky or Reggie-Wheeler, where you're reconstructing the residual field that's much less singular than the retarded field, then you're actually okay. Yeah. Okay, so actually, despite all the difficulties that I've identified for each of these three approaches, all of them have been fully developed for self-force applications. All of them have been implemented in Schwarzschild and Kerr. And to date, everything works, everything agrees. Of course, once you calculate invariant quantities, you have to make the comparison at the level of gauge invariant quantities, because you do have tons of gauge freedom. And obviously, you get different results if you're comparing gauge-dependent quantities. Okay, so that's what you would do at first order, and that has been done at first order, as I say, using all approaches, all three approaches in Schwarzschild and in Kerr. But whenever people were doing that over the years, as I said, they knew this approach breaks down after some time because they're putting in a geodesic source. And the evolving system doesn't stay close to that geodesic source. So people always had in mind, okay, there's going to be some way to import that into an evolution scheme where you don't have a single geodesic source, you're kind of evolving from geodesic to geodesic or something like that. And there's been multiple ways of formulating the evolution. The way I'm presenting here is the only way that's been actually extended up to second order in perturbation theory. And it's not just a way of getting the evolution, it's actually a very convenient way of formulating the field equations. The fundamental assumption that I'm going to make is that all of the time dependence in the metric perturbation is entirely determined by the motion of the puncture and the evolution of the big black hole. So the big black hole is evolving slowly with time because it's absorbing gravitational radiation. So its mass grows with time and its spin changes with time, slowly. So because the black hole is evolving, I'm going to extend my list of slowly evolving parameters. So before I had slowly evolving parameters just associated with the motion, associated with the orbit, I'm now going to extend that list to include the mass of the big black hole and the spin of the big black hole. The evolution equations still look exactly like they did before. It's just now I have a bigger set of evolving functions, curly j. So again, I have these three phases, and then I have slowly evolving parameters. Now, the key step here is going to be that I'm going to treat my metric perturbation not immediately as a function on space-time. So it's not going to depend on some choice of time and spatial coordinates. So say I've got some time here. It doesn't have to be Borel-Lindquist. It's just some time. And then xi is going to be my spatial coordinates. So I'm not going to treat it as just a function of these space-time coordinates. I'm going to treat it as a function on an extended manifold that consists of space spanned by these spatial coordinates, and then phase space, the phase space of the big black hole and the small body. And this is a mechanical phase space. It's not a field phase space. So it's just depending on these phases curly phi and this list of slowly varying parameters. So where time would normally appear, instead, I have a dependence on these phase space variables. And then we get the physical metric on physical space-time by substituting the solution to these equations. So that then makes phi a and ja functions of t, and that's my function h of t and xi. So that's what I was saying back here. The assumption is that there's no time dependence in the metric except the time dependence that's encoded in the orbital phases and the slowly evolving parameters. So how do we formulate field equations for these guys? Well, we just use the chain rule. So when we substitute this expansion, this ansatz, into the Einstein equations, we apply the chain rule. So we get the derivative with respect to the curly phi's times the t derivative of the curly phi's, which is just those frequencies, plus the derivative with respect to j's times the rate of change of those j's. So just ordinary chain rule for this function of these variables, each of which depends on t. Then in this rate of change, I'm substituting this expansion. So that now everything, everywhere in the field equation, is just a function of the curly phi's and the j's. Then I'm going to further assume that the metric perturbation is exactly periodic in each of those phases. So those phases are periodic variables in phase space, and I want to insist that my solution to the field equation is periodic in those periodic variables. So once I say that my solution is periodic in those phases, then I can do a discrete Fourier series. So this is not a Fourier transform in physical time. This is just a discrete Fourier expansion in these phases, capital phi, not capital phi, curly phi. And there should be a tilde on top of that. So then I've removed the dependence on the phases. I've factored it out. And then I've got these amplitudes that are functions of ordinary space and functions of the slowly evolving parameters. This omega k that's appearing as a label here is just a linear combination of the orbital periods, sorry, orbital frequencies. So now once I've got this expansion, my field equations, my Einstein equations, become spatial PDEs for these coefficients, for these amplitudes. And because the rate of change of the orbital parameters is small, it's order epsilon, because of that, derivatives with respect to the orbital parameters are always suppressed by order epsilon, which means they're never going to appear on the left-hand side of the field equations. They're going to appear on the right-hand side as sources. So the slow evolution of the system is sourcing perturbations. But the important thing there is that on the left-hand side, you do not have derivatives with respect to these parameters curly j, which means the equations you have for these amplitudes only involve derivatives with respect to spatial coordinates xi, and you can solve those equations at fixed values of your parameters curly j. So if you imagine just a grid of parameter space, that's what's shown here. This is not space-time, this is parameter space. So each point on there is a list of values of the curly j's. At each point in that grid, we solve field equations that are elliptic type field equations for these amplitudes. From those amplitudes, we calculate these rates of change here, these capital G's. Then we just store all that. So we're storing the amplitudes. So say at infinity, we store the amplitudes at infinity, which is giving us waveform, physical waveform amplitudes. And we store those rates of change, those capital G's, which here I'm just denoting by J dot. So at each point, we solve the field equations, we get amplitudes that we store at infinity, and we get a kind of velocity in parameter space, a J dot, how you're moving through parameter space. Once you've pre-computed and stored all this information, then you just go back, solve these very simple ODEs, which you can solve in a millisecond, less than a millisecond. And that gives you a curve through parameter space, as well as the time evolution of these phases. And then you've got your physical metric perturbation, h as a function of t at infinity, which is just a waveform. So just using pre-computed data, you can generate a waveform immediately, almost instantaneously. And that's important because remember what I mentioned yesterday, a key requirement for gravitational wave data analysis is fast waveforms. You need to be able to generate waveforms very rapidly. And there's actually a package developed by Michael Katz and collaborators that take input of this form and generate a waveform very, very rapidly.
The paper that came out today. The one today that you wrote.
Yeah, so that one today is specifically frequency domain waveforms. The time domain waveforms were a few years ago. Yeah. Yeah, so depends on the complexity of the orbit, depends on the complexity of the signal. For the simplest things, you really do generate the waveform in a couple milliseconds. For very complicated generic orbits where you have a lot of these amplitudes, tens of thousands of these amplitudes, it takes a bit longer, but it's still less than a second, significantly less than a second to generate a waveform with tens of thousands of Fourier modes.
How much time did it take to get all the previous data?
A lot longer, yeah. So the offline step, so yeah, we've broken up waveform generation into an offline step where we compute all this data and store it, and an online step that's super rapid. The bottlenecks in the offline steps are a real challenge here. So let me come back to that. I think I'm going to touch on that here in a few slides, but if I don't, just remind me to come back to it. Okay, so here's an example of a 0 PA adiabatic waveform. So remember I showed you those nice simple waveforms that are just sinusoidal with slowly increasing frequency and slowly increasing amplitude. So that was for quasi-circular orbits. This is for a generic inclined eccentric orbit and has a lot more structure. So it's a lot more complicated, and that's why you get a lot more information out of it. So the technology, or at least the formulation to generate adiabatic waveforms for generic orbits was already known back in 2005, but we only got a true generic in-spiral waveform in Kerr just a few years ago, 2021 maybe. And there the challenge is filling up the parameter space. So you have a lot of parameters in your parameter space. You need to pre-compute a lot of data over a multi-dimensional grid of parameters. So that's 0 PA. For 1 PA, things are lagging significantly further behind. Here's an example. Let's see if this runs. No. Maybe I have to click on it. Ah, this one's showing nice and smooth. Okay, so this is an example where they've taken a whole bunch of geodesic orbits, calculated H1 from those orbits, calculated the force from H1, and then used that to drive an in-spiral. This is equatorial orbits in Schwarzschild, so eccentric, non-circular, but confined to the equator, and non-spinning primary. So this includes all the dissipative and all the conservative information from the first order self-force, but this is not a complete 1PA waveform. In fact, almost everything we're seeing there is pure gauge, because it's only including the first order self-force effects at 1PA order. It's not including this second order effects, the effects at H2. And to get a gauge invariant in-spiral and gauge invariant waveform, you actually need to combine both pieces of information: dissipation from second order and conservative effects from first order. And we have generalizations of this to include the spin force, and the first order force, conservative and dissipative, has been calculated for generic geodesics in Kerr by Martin van der Ment a few years ago. But as I said, this is still missing fundamentally important second order effects. But putting aside waveform generation, people have also done a lot of work on just using first order information to help other sorts of models. So remember this picture we had of the binary parameter space with the different models in different regions. There's been a lot of work on the overlap between different models and using information from one just as a cross-check of other models, but also actually helping other models. So for example, if we calculate first order self-force in the weak field limit, that can actually provide information to post-Newtonian theory. And all of the information from self-force can be fed into effective one-body theories that in principle, once they've incorporated all the necessary information, will be valid over the entire parameter space. So first order self-force information has provided quite a bit of information, very high order post-Newtonian coefficients. Originally, it actually provided a little bit of essential information to complete the 4PN dynamics. The original derivation of the 4PN dynamics was not complete in itself. It took information from first order self-force. A couple of years later, it also settled a controversy where two different groups of post-Newtonian researchers had derived incompatible 4PN results, fourth order post-Newtonian results, and they determined which one was correct by comparing to first order self-force, and that settled the controversy. Okay, but the punchline I'm going to show you is going back to that waveform I showed you in the first lecture that was a complete 1PA waveform. So that is in the simplest case of quasi-circular orbits with a non-spinning primary, non-spinning secondary. So it's non-spinning, quasi-circular. So in that simple setting, as our slowly evolving parameters, we can just have the orbital frequency of the particle's orbit and the mass and spin of the big black hole. I just said the big black hole is non-spinning, but the Einstein equations actually dictate that A dot, the rate of change of A, cannot be zero, but it's small. So what we can do is, if we have something almost non-spinning, we can treat the spin as a perturbative parameter that goes into H1. It doesn't go into the background. That makes it much easier to deal with. And now for quasi-circular orbit, we just have a single phase, which I'm going to call phi p, the particle's azimuthal phase. So that Fourier expansion I showed you now looks like this. We just have one phase here, phi p. We have these amplitudes, and I'm going to decompose into a set of spherical harmonics, tensor spherical harmonics. Everything I'm going to show you comes from Lorentz gauge calculations in Schwarzschild background. So it's Lorentz gauge of first order and second order. We're solving the full set of coupled ODEs, basically for the metric components. So we get ODEs for each of these spherical harmonic modes, radial ODEs. We solve those for a list of orbital frequencies. So that's just a whole bunch of radial ODEs. We put it in, we solve everything through second order. So we write down the second order field equation. Most of the difficulty actually is in computing the source term in the second order field equation, but I won't have time to get into that difficulty. But again, the overall strategy, pre-compute everything, then you get fast waveforms. And these are the waveforms that come out. So which one's which here? Okay, the one at the top is for mass ratio 1 to 10. So that's the same as what I showed you yesterday. And yesterday I didn't show you the 0 PA result. I only showed you the 1 PA result. So here it is for 0 PA, and you see it dephases pretty rapidly. And then 1 PA basically completely corrects that dephasing. Black is exact numerical relativity data. And we can't really do comparisons for mass ratios much above 1 to 10 because there's not enough numerical relativity data to compare against. So we're doing all of our benchmarking at mass ratios basically up to 1 to 15 is the smallest one we've got, or the most extreme one we've got. But we can generate waveforms, instantly for any mass ratio. So this is mass ratio 1 to 10. Everything looks great. This is mass ratio 1 to 1, equal mass binary. Now you're seeing a 0 PA approximation dephase really quickly. On the scale of this plot, you might think, wow, 1 PA is perfect for equal masses. That's amazing. I have a small parameter that's now equal to 1, and I still get a good waveform. That's just an illusion of the scale here. If you zoom in on the late part of the waveform, it's totally out of phase. It's like 6 radians out of phase. But it does happen pretty late. And as I mentioned yesterday, currently our waveforms just break in the late stages when the particle reaches the innermost stable circular orbit. The whole formulation, this multi-scale expansion I showed you, breaks down. You need a different formulation. So we don't expect to have good accuracy in the very late inspiral. Okay, so how long was I supposed to go?
20 more minutes. Actually, 20.
Oh, wow. I was skipping tons of stuff because I thought I was out of time.
So maybe let me repeat my question.
Yes, perfect. Perfect. Yeah. Okay, so for these quasi-circular non-spinning 1 PA waveforms, the offline step took 9 months on 400 cores. So depending on what you work on, that might seem crazy or it might seem like nothing. So compared to numerical relativity, it's still nothing. And once we've pre-computed it, we now have waveforms forever for any mass ratio immediately. But that's a pretty long time, 9 months. For generic orbits, in Kerr, the problem is way worse because you now have a lot of parameters in your parameter space and you need to cover this whole parameter space. So basically, for these 1 PA waveforms, we just have a one-dimensional grid of frequency values. Because even if we're having perturbations that are evolving for the mass and spin of the primary black hole, they can kind of be treated easily separately, and you don't need actually store things on a grid of the mass and spin of the big black hole. If you're in Kerr and the spin is not a small perturbation, then you do need one of your axes and your parameter space to be the spin. The mass you can always just absorb into your overall scale. Doesn't really matter. So there's a lot of work still to be done for generic orbits. I mean, there's a lot of work even putting aside the runtime. There's a lot of work just to formulate and implement things for generic orbits in Kerr. But to give you a sense of the scale of the problem, so I said that Martin van de Ment has calculated the first order cell force, the full thing, conservative and dissipative, for generic orbits in Kerr. He did that for exactly 5 sets of parameters. And each one took multiple days running on many, many cores. And that's first order, which, so in the quasi-circular case, the 0 PA waveform, I can generate all the data on a laptop in, I don't know, a minute, all the data you'd ever need. And then going from 0 PA to 1 PA, you go from a minute to 9 months on 400 cores. So now, if we look at generic orbits and we say, okay, it's a couple days to go from first order to however terrible it's going to be solving the second order field equations. And yeah, we're in trouble, big trouble. So a back of the envelope calculation suggests, don't remember the actual numbers, but in our calculations, the second order, so solving the second order field equations, we need to evaluate a lot of integrals for a totally non-obvious reason. Our calculation of the source term, the right-hand side, turns out, the way we currently do it, to require a lot of integrations over the spheres around the big black hole. And that's what took so long. Actually solving the equation once you've got a source is super fast. It's really calculating the source that takes so long. And when you go from what we've done for quasi-circular non-spinning up to fully generic spinning, you go from the millions of integrals that we evaluated to something like 10 to the 12 integrals. So even if you're able to evaluate these integrals very quickly, that is a really big number. That is a lot of integrals. So there's a lot of optimization that needs to be done before we're going to have what we need for LISA, which is 1 PA fully generic waveforms. And yeah, we've got 11 years to get that done. Okay. Rather than backtrack, I think I'll just end early, but I'll take questions. I'll just summarize here. So as I stressed early on, the mainstream methods of modeling that we use for LIGO, they all break for emeries, and cell force theory that I've described is currently really the only viable method of modeling emeries. EOB, once it takes enough information from cell force, will do just fine, but it needs that information. So you got to do the cell force calculations. And you might wonder, unless you're an EOB person, you might wonder, wait, I've already done the cell force calculation. Why do I need EOB anymore? And for emeries, I'd say we don't, just use cell force. It gives you a fast waveform as it is. What we've also found is even far away from the emery regime, we get pretty good accuracy for mass ratios like 1 to 10. And whether that's surprising depends who you ask. So there's the possibility of actually using cell force waveforms for present ground-based detectors as a independent model to do data analysis with, but that would really require including the final merger and ring down, the final stages of the evolution, and our current formulation of the field equations and everything just breaks before you get there. So we will need to extend everything to include that merger and ring down. The whole method we're using is first principles. I mean, it's an asymptotic approximation, but it's first principles. We're developing everything just from the Einstein equations. But unlike most first principles methods, we can generate waveforms rapidly. So it's unlike the current paradigm of LIGO data analysis, where you have first principle models that then get fed into some phenomenological or semi-analytic model to have fast waveforms. This gives us first principles and fast waveforms together. As we just discussed, there's still work, a lot of work remaining to populate parameter space even at 0 PA. I didn't mention anything about spinning secondaries. I showed you an equation of motion where I had a spin. I haven't showed you any results, but in a sense, that's low-hanging fruit. So there's actually been a lot of work on secondary spin recently. There's been a lot of progress on that because it's so much easier than the other 1 PA effects. So the secondary spin is a 1 PA effect, but it comes in linearly, whereas every other 1 PA effect we're trying to calculate, well, not every other, the hard part is nonlinear. It's much harder. So yeah, if you want to do a self-force calculation or a black hole perturbation theory calculation that contributes to Emery models, try to get in quick on secondary spin, because it's much easier to get a handle on than all the other things at the forefront of the field. For complete 1 PA waveforms, what I'm writing here actually isn't true. I say we only have 1 PA waveforms for quasi-circular non-spinning binaries. That's not true. We have 1 PA waveforms that I didn't show you, I'm not sure why, with a generic secondary spin and a slowly spinning primary. So it's not totally generic spin. The spin of the primary is aligned with the orbital angular momentum, and you have a little tiny bit of planar precession coming from precession of the secondary's spin.
What's the spin you'd expect of primary?
High. So for an extreme mass ratio, your primary is going to be a massive black hole at the center of a galaxy. And we won't know until we see these things really what the spin is. But a lot of just electromagnetic observations suggest that those spins are high, like over 0.9. We don't know if those measurements are going to hold up once we actually detect these, but we do expect fast spin. We also expect significant eccentricity. So everything we see with LIGO, or almost everything we see with LIGO, everything's quasi-circular. And numerical relativity spent many, many years trying to make it as quasi-circular as possible. You do a lot of work to get rid of eccentricity. For Emery's, we don't expect that at all. We typically expect pretty high eccentricities. And depending on the formation mechanism, you can also have very significant inclination as well. Okay, so yeah, I think I'll just end early and take any questions.
So we have a lot of time for questions.
Yeah.
One point, if you have a black hole and if you have your study particle orbit around it, if this particle has spin, then do you still get those mid-planar orbits in the planar orbits, or they are not planar? If the particle has spin.
It depends on the direction of the spin. With respect to okay, do you have a spinning primary as well? Okay, so you can still have perfectly equatorial orbits if your secondary spin is aligned with the primary spin and the orbital angular momentum is also aligned with the primary spin. If all the angular momenta are aligned, you have an equatorial orbit. As soon as you have any non-alignment between any of these three vectors, then you start getting planar precession, non-equatorial motion.
Now, are people comparing the eccentric waveform of
So comparisons between post-Newtonian and self-force are very easy and very well developed. Comparisons with numerical relativity is much subtler because you have to make sure that you're actually looking at the same physical system, and eccentricity it's just a choice of parameter. You can choose different versions of eccentricity, and you need to somehow make sure that you're choosing the same ones. So I showed you in the first lecture that that estimation of the accuracy of all your different models generated by Martin van der Ment and Harold Pfeiffer, that was based all in quasi-circular orbits. They have since done the comparison with eccentric orbits, and they found a compatible level of accuracy that they found for quasi-circular. So again, the self-force method appears to cover more of the parameter space than you might expect, even for eccentric orbits. But I also mentioned yesterday that their original prediction was a bit over-optimistic. So we won't really know the accuracy until we do the full 1 PA eccentric orbit calculation. Yep.
I have a bit of a technical question. So you mentioned that solving these ODEs is actually very fast.
Yeah.
So they look like the sort of radial ODEs you get for normal modes.
Yeah.
And solving them with like a shooting method, I thought requires quite a lot of sort of analytic control in.
Well, okay, so quasi-normal modes are more complicated because you actually have a vacuum solution, but you're imposing boundary conditions at both sides. Here, things are much simpler at the level of the ODEs, because so in that case, you need to find the frequencies that give you regularity of both sides.
Yeah.
In this case, all the frequencies are coming from the orbit. Every frequency that enters into the field equation is just a linear combination of your orbital frequencies. So you just know those numbers, you just put them in. And so that eliminates much of the challenge that you have for quasi-normal modes. And then you just impose ordinary boundary conditions, outgoing waves at infinity, downgoing waves at the horizon. And depending on what slicing you use, those boundary conditions take different forms, but they're always physically that. Anyway, it's just a second order radial ODE for each mode. I thought I saw a hand up there.
You were showing us how the curvature scala psi4 was entering H1, I think it was.
Yep.
I was wondering how do the other scalas enter into the perturbation that we know that they enter,
So this depends on whether you're in Schwarzschild or Kerr. So generically, psi0 and psi4 are the only gauge invariant ones. And even then, they're only gauge invariant at first order, not at second order. But even at second order, you can get, in a certain sense, most of the metric perturbation from psi4 or psi0. What I showed you was a gross simplification of that, where I just took this curvature scalar and applied a linear operator made up of integrals and derivatives. In fact, that doesn't give you the full metric perturbation. You need to add something on top of that. But the thing you add doesn't involve solving any PDEs. It's quite simple to calculate. Now, if you're trying to, and that gives you all the information, the full information. So you get most of the information from psi0 and psi4, and you get a little bit more information from this thing called the corrector tensor. Now, if you're in Schwarzschild, one of those Reggie Wheeler's really variables is actually the imaginary part of psi2. And you can get the same information from that as you get from psi0 and psi4. You get basically all the same information from different methods. And in fact, so the real part of psi2 is gauge dependent, even in Schwarzschild. But the other Reggie Wheeler's really master variable is the real part of psi2 in a particular gauge. And again, that's giving you most of the information in the perturbation. Whatever you like. So we're always going to be using principal null direction aligned tetrads, but other than that, just take your pick. So most people would use Kinnersley. Sometimes we use Carter, if you're familiar with that one. They're all the same because they're aligned with the principal null direction. So all you're doing is scaling L and N. Otherwise, it's the same. Yeah.
There are sufficiently far away that I guess it's not a big deal, but at the resonance, could there be some substantial?
Yeah, so the main impact, if you do have an external environment, the main impact it has is in tidal resonances. So the external environment is creating basically an external tidal field applied to the entire binary. And then you can have tidal resonances that do have an observable effect, yeah. If there's an accretion disk, you can also have, drag that's also doing things. Did I see one more hand? Yeah.
Can you recall in what way this spinning particle, the circulating particle, experiences the gravitational field of black hole and its own back reaction?
So its experience of the gravitational field of the big black hole is just the geodesic equation.
But you said that you surround this particle, the world line of this particle with Q, and then define some metric tensor inside Q.
Do you mean the residual field? Is that what you mean?
Or this is yet another.
Not sure which thing you're referring to. So we have the metric perturbations, H1 and H2, they're the physical metric perturbations. Specific pieces of those, the regular field or the residual field, affect the motion of the particle. And at first and second order, that motion is geodesic in this effective metric G plus HR. So it's in free fall with respect to a particular effective metric.
Right, and this effective metric is what?
G plus HR. So remember when I was solving field equations using matched asymptotic expansions, HR was just a particular piece of the solution in the vacuum region around the small body. There's a particular piece that it's not just smooth at the point particle, it's a vacuum solution at the point particle. Yeah. So it's really something that if you're just sitting there at the particle, you would perceive it as an external tidal field. Just an ambient external field around you. One more? Yep. Yep. Yeah, very big role. So again, the common gauge choices are Lorentz gauge, Reggie-Wheeler gauge, and radiation gauge. So radiation gauge is the gauge that you get when you reconstruct the metric perturbation from psi 0 or psi 4. So these are the common gauges. Lorentz gauge is the one that's nice around the particle. The other ones, if you're getting the full metric perturbation in these other gauges, you always have some singularity extending away from the particle, which is not so nice. But we know how to deal with that, and calculations have been done in all of these gauges. You can also do a mixed kind of puncture scheme that's also been done and works fine, where you put the puncture field in a gauge that is represents the singularity nicely, so say the Lorentz gauge. But then you put the residual field in a gauge that's convenient for solving the field equations. So for example, you can get the residual field in the radiation gauge and the puncture in the Lorentz gauge, and then you have a nice combination that's good for the singularity and practical for solving the field equations. Okay, I think
So let us
that's everybody.
take a-